Hey guys, welcome back to Genius Learning. So in the previous problem, in the previous video, we saw that we can use the vector displacement equation in different ways, and we can combine segments in order for us to complete a right triangle, which is what we need to use our trig identity. So let's see how we can do that for this particular problem here. Okay, we have this softball player or baseball player, and she hits the ball at a 45-degree angle. Okay, this is the trajectory, and 188 meters away is how far the ball went, and we want to know this question here. Okay, so this is the same drawing as that one, and we need to find the velocity initial needed to hit the ball at 1.9 meters above the ground, which is right here, at a distance of 188 meters away at an angle of 45 degrees. Okay, so what is the velocity initial needed in order to make the ball reach this area? Okay, so we're going to start off with what we know. Okay, we have our displacement vector equation, and so we know what to do. Let's draw our triangles here. And so the place that we're interested in is right here. This is our final x, right? And so for our displacement vector, we draw a line straight to our final position. This is the position that we're interested in, and so that's where we go to first. Okay, then the next term here, velocity initial t, we follow the arrow, the initial velocity arrow, and we go all the way up till we're vertically aligned with the final position. Okay, so this here is velocity initial t vector, and this last part here is always in the vertical direction going down, which represents 1/2 gt squared. All right, so in this problem, again, it's kind of clear to see that this is not a right triangle, and in fact we can't use this triangle here in orange because this vector is going right through the angle, so we can't take advantage of that angle. And so if we stretch it out and we include this segment, which is the 0.9, right? I'm gonna highlight it. If we include that segment, now we have a triangle that we can work with. Okay, and so we just need to make sure it's a 90-degree angle, and now we can work with it. Okay, so let's use the trig identities that's gonna help us get what we need. And we have the x component here, and we know all the values on this side here. I'm sorry, we don't know all the values here. We don't know t. Okay, so why don't we do tangent? Okay, we're gonna do tangent theta, all right, and that's equal to opposite, which is the entire side, the entire opposite side here, which is 1/2 gt squared plus this extra segment that we're adding on here, 0.9, over adjacent, which we do know, and is 188 meters. Okay, so let's solve for time to see how much time it takes for this ball to get here. Okay, so if we solve for time, we're gonna have 188 tangent theta. Okay, we're gonna pass this 0.9 to the other side, so minus 0.9, and we'll leave this 1/2 gt squared here. So multiply everything by 2 and divide by gravity. So here we're going to have 188 tangent of 45. okay, minus 0.9, that's the left side. So I'm gonna put parentheses around everything and multiply the 2 over and divide by 9.8. Okay, we're gonna be left with a t squared, so we're gonna square root this side. And now we have our t value, okay? So putting that into your calculator, you should get 6.17 seconds. And this represents the amount of time it takes for the ball to travel to this point here, okay? Now, let's find the velocity needed to make that happen. Okay, so we know how much time it's gonna take. Let's see, with these conditions, what the velocity needs to be in order to satisfy those conditions. Okay, so let's use, again, our displacement equation. So like I said, this is gonna be important, and so important, I think that you should memorize that. If anything, just the 2 vector equations for projectile motion. And we can derive other things from it, but we're gonna use it to find the velocity initial that we need. And so let's choose, remember that we can make this either x or y equation. So let's solve it for x, right? So we got the change in x is equal to the velocity initial in the x times time plus 1/2 ax t squared. All right, we know that there's no acceleration in the x direction. And we also know that by breaking up this here into components, right, from previous examples, that v initial in the x is v initial cosine theta. All right, and then the time comes down, and this side here is x final minus x initial. Okay, so initial position started at 0, so this part here we don't need. And now we have an expression that we can use to find the initial velocity. So x final, or just x, divided by, we have cosine of 45, and the time that it took to get to this point, 6.17 seconds. And that's equal to velocity initial. The x is 188 meters, so let me just rewrite that. Velocity initial is equal to 188 meters, which is the one on top, cosine of 45, and the time is 6.17 seconds. All right, so plugging that into calculator, we should get velocity initial is equal to 42.8 meters per second. Okay, that's pretty fast. And so let's keep that in mind when we're gonna do the next part now. All right, so let's find the height that this problem here is asking for. Okay, so we're gonna move on to this problem now, and we find that we're gonna be able to find the exact height above a certain segment, let's say a wall. And using the vector triangles, we're gonna combine one more piece to it, so we're gonna add on to it now. So how far above the fence will the ball be if the fence is 3 meters high? So let's draw a fence here, let's say, okay, that's 3 meters high. You know, like you're playing baseball, and then let's say that's the, you know, that's the wall that goes out. And it's asking us how far above this fence, that's 3 meters high, will the ball be hit? Will the ball go if it's hit with a velocity of 42.8 meters per second at a distance of 116 meters away? So this is 116 meters away. Okay, and the velocity initial is equal to 42.8 meters per second. And we want to know how high above this fence will the ball be. Okay, so we're going to draw a line here that represents an initial height above the 3 meters. Okay, and just so you know, this H is not drawn to scale, and so you'll see what I mean when we go to solve it, but just know that it's a height above the wall, and that's what we're interested in. Okay, so let's see. Let's use our vector equation, right? Like always, let's make our triangle. Where is our point of interest, right? The displacement vector always goes to the point of interest, or the final position that we're interested in. So the final position that we're interested in is a height above the 3 meters. And so if we go right to it from the origin, this is the displacement vector. All right, now our second vector is going to be vector initial times t. We follow the initial vector here and the initial velocity, and we follow it all the way to a height right above the final position that we're interested in. Okay, so velocity initial times time, and then finally we have the last term, which is the gravity term, which always points downward. All right, 1/2 gt squared. All right, so again, it's kind of easy to see that unless we combine something about these triangles, that this triangle up here is not something we can use. Again, it's in the middle of the angle, and it's not anything we can use, not even if we combine just the h, you know. So if we combine this segment with this piece here, we can't use this 45 degree. It has to be flat on the ground. So I'm going to combine this entire side here. All right, I'm going to highlight each segment there, and then this entire side here and the entire bottom. All right, so I'm going to make sure that this is a 90 degree. So there you can see the big triangle that we just made, combining 3 segments now in order to find a height above this wall. Okay, so what can we use? Let's go for tangent, because we know that we have the adjacent, and so whenever we have the value of the adjacent, cosine or tangent come to mind. And so I'm gonna go with tangent, and let's see what we get. So we're gonna do tangent theta is equal to opposite, which is this entire side now. Okay, so we have 1/2 gt squared plus the h, which is the height above the fence, plus the length of the fence, or the height of the fence, right, 3 meters, over the adjacent, which is 16 meters. All right, so now let's solve for h, because we want to know the height above the wall. So we're gonna pass the 116 over here. We got tangent of 45, right? Let's pass this term over, which is minus 1/2 9.8 t squared, and we'll pass this term over, which is going to be minus 3, leaving us with h. Okay, the time that it takes to get there, we're going to use the time that we calculated. No, because this is 116 meters. Okay, so we need to leave this equation here as is, because we have 2 unknowns. All right, so let's solve for time. So let's get this solved in order for us to solve the height. Okay, so sometimes that happens. You don't know which comes first. You gotta solve for the time or you gotta solve for the height. And so this is fine. We leave this equation here and we realize that we need to solve for time at 116 meters away with this velocity here, looking for that height. Okay, so that's gonna be different from this one because this one is at 0.9, 188 meters away, has a certain time, which is not the same as this. Okay, so let's find the time here. And we're gonna do that with the displacement vector again. And let's solve it for the x. Okay, so we're gonna use the displacement vector. Okay, and let's solve it for the x. So we have the change in x is equal to velocity initial in the x times time plus 1/2 ax t squared. There's no acceleration in the x. All right, this is final minus initial. Velocity initial in the x, we know that that looks like velocity initial times cosine theta, right? We derived this already. Times time, and we have the change in x here. All right, so now we're able to solve for time. So let's pass this velocity initial cosine over to the bottom. Okay, and we have our t equals the displacement, which is 116 meters away, our velocity initial, which is 42.8 meters per second, and cosine of 45. Okay, so now we're gonna get a time that is very specific to the conditions that we have. We have a displacement 116 meters away. We have an initial velocity of 42.8, and we have an angle of 45. And so with those conditions, the time that we get is t equal to 3.83 seconds. Okay, so all of this was to find time, but now we need to plug in this time here into here. Okay, so plug that into there. Once we do that, we'll have all the values here and we'll be able to solve for our height. Okay, so let's do that. Let's move everything over to here. So I'm gonna rewrite this. We got h is equal to 116, tangent of 45 is 1. So to save some space, I'm just gonna not write that. So I'm gonna write 116, tangent of 45 is 1, so we don't need to write it, minus 1/2 times 9.8 times the t that we found, which is 3.83 seconds squared, minus 3. Okay, so perfect. We have all the values that we need. When we plug that into the calculator, we're gonna get a height of 42 meters. You may be thinking, man, that's really high above this 3-meter wall. So you see now why I told you this is not drawn to scale. But if you think about it, this is a fast velocity for a ball to travel. And you got a pretty good height here. 45 degrees is pretty much the best angle that you can hit something at in order for it to go its farthest. So it traveled a pretty good distance. More importantly, this is really fast and the angle is really high. And so this answer makes sense because these initial conditions are such that, you know, it would go really high above a 3-meter wall. Okay, so this h here is equal to 42 meters, which is, you know, a lot bigger than it's drawn, but everything here makes sense now. So let's recap on the first part here. We found the velocity needed to hit the ball at distance of 0.9 meters above the ground, 188 meters away at 45 degrees, right? We use our vector triangle and we combine this segment here in order for us to take advantage of a 90-degree triangle in blue, right? With trig identities, a couple steps, and we have the time needed to reach that spot, okay? Now, to find the initial velocity needed, we look to our dear friend, the vector equation, and we replace it with the x, because remember we can do either x or y. So we're gonna use our x, and once we plug in our values, we see that we can solve for velocity initial, and 42.8 meters per second is what we got. Now moving on to the next part of it, it's very specific in asking how high above a 3-meter fence will the ball go if it's hit with a velocity of 42.8 at an angle of 45, a distance of 116 meters away. And so again, we use tangent, and you don't know which part you need to do first sometimes, so we just blindly went into trig identity, and then we quickly realized that we have an unknown and our h is unknown, so two unknowns. We're not able to solve this, but we box it up and we solve for the t separately using again our vector equation and writing it out for the x values, right? We find that the time needed with these conditions for this problem is 3.83 seconds, right? Once we found that time, now we can plug it back into the equation we had found before, and all these values are known, giving us a height of 42 meters, which is pretty high. That girl's pretty strong, man. So the next couple problems are gonna be similar to these. So let's take a look at what we got.